try and address this question, which is rather a large question for a lot of people at the moment. Hopefully by the end of my talk, you'll either go, oh, maybe, or yes, they are very important, whether physically or chemically. Just to acknowledge a lot of collaborators, people have helped me in the past 5 years, 6 years. During my PhD, my supervisors were Gemma Wadham and Martin Tranter. They really got me into this bum fight. It is a little bit of a controversial area. Leanna Benning and Rob Raiswell at the time were both at the University of Leeds, and I did a lot of my work up there with those two. Whole host of collaborators helping with things from silicon isotopes to sample access to trace metal analysis. Various students that I've worked with in the last few years who have really produced a lot of the recent data, and many people for help during many months in the field in Greenland and Patagonia. So here's what I'm going to try and address. I'm going to talk a little bit about glaciers, what they look like inside, why they're important biogeochemically. I'm going to talk about my past research, so that's the research that I was doing in Bristol during my PhD. Then I'll talk about my postdoc research, the one that I just finished back in October, and hopefully summarise and take questions. So why are we interested in glaciers? Bristol has a glaciology centre. Some of you might think that's quite strange because the UK doesn't have any glaciers of its own, but it has a very active glaciology community. We're interested in Bristol, or I was interested, I'm no longer in Bristol. We're interested in Bristol about glaciers because they're quite an important component of the hydrological cycle. And terrestrial biogeochemical weathering as well. They cover around 10% of the land surface area at present. During the last glacial maximum, ice sheet cover looked something like this. That was only 21,000 years ago, covered up to 29% of land surface area. And a lot of these ice sheets, especially over northern Europe and northern North America, melted very quickly as well. In the past, they were also potentially very important. Neoproterozoic glaciations, also known as snowball earth glaciations, they might have covered up to 100% of the land surface area. And this is also a part in time where you get these really interesting iron-banded formations form, and some of these iron-banded formations have things like glacial drop stones. So potentially in the past, there's also some questions that we might try and answer. Glaciers discharge about 2,000 to 3,000 or 2,500 kilometers cubed of fresh water into the oceans every year. Around half of that is through icebergs. In Antarctica mainly, but also in Greenland, that's very important. And half of that is in freshwater runoff, so glacial meltwater streams. At the moment, people are most concerned really with these alpine glaciers because they're melting very rapidly and they're contributing most to sea level rise at the moment alongside the Greenland Ice Sheet. But over the next few decades, we're going to be mainly concerned with the two big ice sheets because they hold a huge amount of fresh water. In terms of sea level equivalent, it's up to 65, 70 meters of sea level equivalent. So for places like Tampa, that's incredibly important, obviously. Glacial 101, some of you probably know this already, some of you maybe don't know so much of this, but the ice sheets, the big ice sheets, and a lot of glaciers as well, temperate glaciers and in the mountains and whatnot, underlined by fresh melted water. So in Greenland, we only really understood this in the past 10, 15 years really, but much of Greenland is lightly thawed at the bed. That means there's liquid water there. And Antarctica, you've probably heard a lot about this from the Sousa guys, but more than 400 subglacial lakes have been identified in Antarctica. That's up from maybe 100 in the early noughties, and really only Lake Vostok was identified going back into the 80s, I think. So there's really been an explosion of subglacial lake identification in Antarctica. And obviously recently, 2 of those subglacial lakes have been drilled into. So Sousa, so Lake Mercer in January or December, January, and subglacial Lake Whillans, which was in 2013.
John?
Yes?
Is that connectivity in Greenland that clearly done so that, what, 30% is actually freshwater flow, and in
terms of
Antarctic, it's obviously quite a bit less.
Well, yeah, I mean, a lot of questions to ask about Antarctica. I mean, a lot of these subglacial lakes are thought to be connected or interconnected. There's a lot of evidence as well of subglacial meltwater rivers actually discharging into the ocean as well. These imprints upon some of the ice shelves are where subglacial meltwater is thought to have exited from the ice sheet. That could be from subglacial lake drainage events. We have A lot more knowledge of where the water's coming out in Greenland, obviously, because there's a lot of land terminating glaciers. A lot of this work is so new, actually. Go back 10 years, and a lot of people didn't actually think there was any meltwater at the bed of well, they thought there might have been some meltwater at the bed, but it was only there seasonally. But now, with the advent of all this, satellites and remote sensing techniques, it now appears that there is quite a bit of meltwater at the bed of Greenland. Some of this might be seasonal, but I'm sure a lot of it is there year-round as well. So when you cut open a glacier, these are based on schematics from Chu, 2014 paper, and based on the Greenland Ice Sheet mainly. When you cut open a glacier, this is kind of what it looks like. You've got lots of different systems going on here which are competing against each other, and what makes sampling at the terminus difficult sometimes to identify which parts of the system are contributing what. In the summer, you get this superglacial meltwater system open up as the summer heat melts snow and ice. You get superglacial lakes form, moulins form. These drain meltwaters from the surface to the bed of the ice sheet or to the bed of the glacier. And here they join this, very early in the season, we call it a distributed network, which is an inefficient drainage system. The more meltwater that flushes into this system increases the efficiency of this system. And it's thought that channels start to form subglacially to efficiently move the water from the surface through the subglacial system to the glacial portal, and then over a meltwater, or over a proglacial meltwater river and into fjord systems mainly. So these are what these superglacial lakes look like. These are actually very important for driving the subglacial hydrological system. They can drain in very rapid timescales, and over in a couple of days, a superglacial lake that's a couple of kilometers wide can drain through these moulins into these subglacial systems, and out the front. This is where we measure all our geochemical profiles. And this is what a meltwater river looks like in Greenland. This is the one we've gone to since 2009, actually, before I was a student. But we were there last year as well. This is Leverett Glacier. This gives you some idea of the evolution of this river over a melt season. It goes from a trickle, a stream that's probably about a meter cube per second, to peak melt, where you're talking about 400 to 500 meters cubed per second. I always compare that to the River Thames, because the River Thames is about 100 meters cubed per second as it goes through central London. But that's very difficult to do to Americans unless you've been to London. And this is how we measure our discharge. We use this fluorescent dye called rhodamine, and we do something called dye dilution. And that means we can generate these really nice time series of discharge in some of these proglacial rivers. And then these turbid proglacial rivers exit into fjords and their coastal systems, and they make these nice buoyant sediment plumes in certain places. To quickly contrast, this is what a marine terminating glacier like, or tidewater glacier looks like. The main difference here is that this subglacial meltwater channel comes out at depth, and it could be 100, 200 meters at depth, where it entrains oceanic waters, and then rises a buoyant sediment plume, or buoyant turbid plume. And they also discharge icebergs, which is important for iron cycling, or potentially important for iron cycling, as I'll talk about later. And these are what these hydrographs look like. So you go over a season, you get very big changes from hardly any meltwater in the stream at the beginning of the summer melt season, up to 500 meters cubed of meltwater flowing through these rivers, and back down to pretty much nothing by the end of September, early October. And these are some SF6 traces that we've been doing. This was in 2012, looking at the evolution of these subglacial hydrological systems from inefficient systems at the start of a melt season. And the more water you flush into this system, the more efficient the channels get underneath the glacier, and the more efficiently water is pumped out to the front of the glacier. And that's very important in terms of the geochemistry as well. Going back to 1991, this is a photo from Martin Tranter when he was, this was basically this glacier. It's called Old Glacier de Rolla in the Swiss Alps. The UK glaciology community went to test ideas. And this is the first subglacial sample that was retrieved and tested for geochemistry ever, that I know of anyway, and that Martin claims, but that's there for some context. And it also gives you some context, as this is quite a new field as well, really. Early 90s, I mean, it seems quite a long time ago to people were maybe 21. But for me, I was alive during this time where they were collecting some of these samples. Some quick points about glacial biogeochemical weathering. The most important thing, I think, is that you get this really intense physical erosion happening underneath glaciers. They move, they crush bedrock, and that exposes these trace reactive components in the bedrock that might not be exposed otherwise. And these trace reactive components dissolve very quickly, things like carbonates, for example. You can get trace carbonates in bedrock, and that might imprint more on the signature of the water than silicate rock. It also grinds these rocks into fine powders, which are very geochemically reactive as well. And that forms part of my story later. There's a whole range of geochemical reactions occurring underneath the glacier and in front of the glacier. And there's a whole range of redox gradients that are potentially going on underneath the glacier as well. We published a paper at the start of this year showing that this catchment in the Greenland Ice Sheet is super saturated with methane. So there's methane being pumped out from underneath these glaciers. And that methane, according to the isotopic signature of the methane, is from microbial methanogenesis as well. So there are active ecosystems living underneath these ice sheets and glaciers, and they're doing funky things. Some of this stuff actually goes back to the 1970s when people were looking at proglacial terrains and trying to infer things about past glaciations. And this guy called Hallett published a couple of papers in the 70s looking at amorphous silica precipitates on old bedrocks and carbonate precipitates on old bedrocks. And this is way before we actually really knew anything about subglacial chemical weathering. And I just thought this was interesting going back in some of this literature in hindsight of some of the stuff that we've worked on. But yeah, as I said, huge quantities of sediment are eroded from underneath glaciers. This doesn't necessarily apply to Antarctica, but I'll talk about why that might be later. But typically in a lot of proglacial rivers, you get more than a gram of litre of sediment. And that's pretty much an order of magnitude higher than non-glacial rivers, or most non-glacial rivers. So we've kind of become quite interested in what the impact of these waters coming off the ice sheets might have on downstream ecosystems. And mainly that's through the delivery of nutrients. And pretty much going back into the early noughties, we had no idea about whether glaciers were important at all. And a lot of elemental budgets, they're pretty much ignored. And that's kind of like obvious, really, because you think, oh, it's an icy environment. The water's very, very pristine. And Antarctica, you know, people pretty much didn't mention the ice sheet when they were talking about fertilization of the Southern Ocean or iron inputs into the Southern Ocean. And that's still a little bit controversial now. But we're interested in it because we think that glaciers might be influential, certainly on the regional scale, be it physically or chemically, and might have some, and glacial meltwater might have some influence on the things like the biological pump in the oceans, or in fjords anyway. There's also all this circumstantial evidence to suggest that glacial meltwaters might be quite important. These might be algal blooms off glaciated regions like the Gulf of Alaska, which is typically iron limited, also around Greenland, Disco Bay, and also the occurrence of some major fisheries downstream of some glaciated terrain as well. And there could be obviously lots of different reasons for that, but we think glaciers might be playing some role in that. So I did a little search on Web of Science because I was kind of interested a few months ago about how many papers were coming out related to this, and to show you really how recent this field is, but also how it's sometimes interesting to try and look back into the past and see if anyone was looking at this 30, 40 years ago. And there was this one paper, and I thought, oh my God, like people were doing this 30, 40 years ago. Well, I'm late to the game. And this was a paper published in 1973. Only had one author in Science. This paper was trying to argue that glaciers actually are really important for fjord biogeochemistry because there are elevated silicate and nitrate levels in the one glaciated fjord compared to a deglaciated fjord, and that equated to more prime production. But I just wanted to show to you as well how like this field is really kind of shooting off in the last 10 years or so. People are becoming more and more interested in this. And that's led to a whole load of publications talking about elemental cycle in glacial meltwaters and underneath ice sheets and glacier and melting glaciers and polar glaciers. So the big question that we wanted to ask was, are there differences between meltwaters and icebergs in nutrient delivery? How much of each nutrient is being delivered to the near coastal systems around ice sheets and downstream of glaciers that might discharge into near ocean ecosystems? What form is it in? Is it dissolved, colloidal, Is it particulate? I mean, the particulate one really stood out to me because the amount of sediment being transported by glaciers and what happens on delivery to coastal and fjord environments. And this is kind of where it gets a little bit controversial because as with rivers, these two might not actually be that important if the stuff that goes into the fjords doesn't get out into the open ocean, or the stuff that goes into the fjords gets deposited and buried very quickly. So I'm going to talk I'm going to talk a little bit about a lot of my PhD research really, and some of my early postdoc research. This is on nutrient export from the Greenland Ice Sheet from this catchment called Leverett Glacier. I'm mainly going to talk about iron for the sake of time, otherwise you'll be here all evening and you'll get very bored with me. So the Greenland Ice Sheet, just to put it in context, compared to some of the great Arctic rivers, it discharges in terms of freshwater as much as most of the major Arctic rivers. In terms of sediment, it really is a really important sediment generator in this region. Paper that came out in 2017 was suggesting that despite covering about 1% of land surface area, or 1% of land surface area, the Greenland Ice Sheet is actually responsible for around 8 or 9% of sediment export to the oceans globally. So a really, really big hotspot for sediment export. And we had 2 study sites that we went to. This is Leverett Glacier that I've talked a little bit about. It's quite a large catchment, or what we would call a large catchment. It's got a big proglacial river in the summer. And this is Kiatuk Glacier in southern Greenland. This actually has many, many names depending on where in Greenland you are and who you talk to. But we've called it Kiatuk. We've tried to stick with that name. In the literature, there's about 5, so it's difficult to find much out about this glacier. This is a much smaller glacier in southern Greenland. And we kind of wanted to contrast a large glacier with a small glacier because there could be some differences in the biogeochemistry of the rivers exiting these 2 different systems. In terms of iron, this is what we're really interested in classifying. We want to have a look at the truly dissolved fractions in the meltwaters. This is stuff that's ultra-filtered through a 0.02 filter. Total pain to do in the field because it goes very, very slowly. Then there's kind of the more traditional dissolved iron classification, which is through a 0.2 or 0.45 filter. And this actually includes a lot of colloidal and nanoparticulate material. So by getting this, it doesn't really tell you anything in glacial meltwaters anyway about the truly dissolved fraction of iron. And then there's this stuff that's bound to sediments. And this is stuff like ferrihydrite, which is a freshly precipitated iron nanoparticle, and it's more aged iron nanoparticles as well, like goethite or hematite. And these minerals are really, really important in the iron export from ice sheets as I'll go into. To look at the surface, is there any iron in the surface? Well, we've taken some samples, and iron concentrations tend to be very, very low in the surface compared to bulk meltwater outflow streams. So what I really wanted to emphasize here is the iron isn't coming from the ice sheet surface. This is where a lot of the meltwater is being generated, but this meltwater at the front of the glacier is not coming from the surface, even though 99% of the water in that river is coming from the surface. So something's happening between the melt on the surface when it drains in the ice sheet and when it comes out. The surface is important, as I mentioned earlier, for the subglacial hydrology, because the surface melt drives the subglacial hydrology, flushes out waters from the bed, flushes out sediments from the bed. Subglacial weathering environment, this is where most of the business happens. Oh, that's gone away. But there's some evidence in the past that the subglacial environment is indicative of generating very high iron concentrations. And these might be kind of, I would call them special sites, such as this is Blood Falls in Antarctica. This is a subglacial iron-rich ferrous brine exiting Taylor Glacier in the dry valleys. This is an exceptional example, but it just shows you the potential for glaciers to be able to generate large iron concentrations in these redox gradients. This is an ice core from Greenland, and these guys were actually really surprised. They drove through the ice sheet and hit the bed, and they didn't expect to find any water there, but meltwater at the bed flooded the borehole. It let it refreeze, and they took out that refrozen water, and it was this kind of rusty iron color. So we measure at the front, and other people have done work on this in the past as well. Pete Statham did it with Martin Tranter and Mark Skidmore. It's kind of the earliest measurements of iron in glacial meltwaters. Maya Bartier and the Woods Hole crew published a paper in 2013 showing very high amounts of iron in glacial meltwaters. This is our work from those two systems I was talking about, the small system and the large system. This is the truly dissolved iron, and this is the colloidal nanoparticulate iron, stuff that goes through a 0.45 filter. And there are really high concentrations of iron in these meltwaters, up to 4,000 nanomolar in the colloidal nanoparticulate phase. And these high iron, this is actually, if you showed this to someone studying silicate weathering and looking at maybe like sodium or potassium concentrations, they would start really high early in the melt season and go off as they're diluted down. So this is in contrast to a lot of the other key geochemical indicators. So a lot of this stuff is being flushed out of the ice sheet bed later in the melt season. These shaded areas are what we call outburst events, and these are changes in the subglacial hydrology as a result of melting, or as a result of superglacial lakes draining through the ice sheet very rapidly. So these lakes drain very rapidly, hit the bed, they induce a big hydrological shift in the bed, but they also flush out a lot of freshly weathered bedrock, both physically and chemically. And they're driving these very high concentrations of this colloidal nanoparticulate phase.
John?
Yes.
So if you could dissolve in the early part of the year, obviously it's quite high.
Yeah.
What is the residence time of the water actually in those subglacial lakes? I mean, are we looking at reactivity that is occurring over the winter time to release dissolved iron as opposed to colloidal iron?
That's a good question. So right at the start of the melt season, when you're getting these distributed waters coming out of the glacier, they tend to be much saltier. I say saltier. They've got irons dissolved in them. That's right at this part. Actually, there's not a huge amount of iron at that part of the season. But the residence time of those waters is thought to be quite long because they've been sat there over the winter. And the waters have been sat there in contact with this freshly ground rock. But actually, they're not. The opposite side or the flip side of things is that there are subglacial meltwaters across the whole catchment all year round, even in the winter. So for Leverett Glacier, that goes up to about 60 kilometres inland, which is a hell of a long way inland. And it doesn't always go that far inland as well. It's only in recent years that it's drained that far inland. So some of the waters that might be draining out later in the season, say up here, might have been sat there for a long time. We just don't know. But a lot of the usual geochemical indicators we use to trace long residence time meltwaters just get diluted out by all that superglacial melt. But for some reason or another, iron doesn't seem to, and it's probably because they're very, very high concentrations. There's also probably some of this is freshly weathered bedrock as well. I don't think it's all these long residence time waters, but for sure, I think some of these are long residence time waters. Probably one of the most important components of this whole story is the sediment, or for me anyway. This is something that no one really had looked at in the past, and I really wanted to have a look at the suspended sediment because there is so much sediment coming off these ice sheets. So we did some iron extractions. We used the ascorbate method and the dithionite method. And these are quite selective for certain iron nanoparticles. Ascorbate extracts pretty much only freshly precipitated ferrohydrite. And ferrohydrite is thought to be at least partially bioavailable in incubation experiments. So that's quite important for delivery to marine environments. And the concentrations we were getting were actually really, really high. We were kind of surprised how high these concentrations were. And if you kind of use the back of the envelope calculation and you scale these kind of concentrations up to the whole of the ice sheet, then the amount of ferrohydrite coming off the ice sheet is actually huge quantities coming off in these sediments. We also looked at the nanomineralogy of these sediments. This is something I'm really keen on doing. So trying to look at these nanoparticles under the transmission electron microscope, and also trying to look at the speciation of some of these particles, because there's evidence to suggest that particles rich in iron 2 species might be more bioavailable than particles rich in iron 3 species. And actually in these subglacial, or in these suspended sediments coming from subglacial systems, there's a hell of a lot of iron 2 dominated particles. And some of these might be primary silicates, but we're also finding with transmission electron microscopy that some of these nanoparticles that we thought were ferrohydrite, which is thought to be an iron 3 mineral, actually had a lot of iron 2 in. And there's some recent indications that some glacial sediments in Patagonia are also packed with iron 2. And when Elizabeth Schoenfeld did these incubation experiments with marine diatoms, she actually found these iron 2 rich glacial sediments had a much bigger response to these diatom communities than iron 3 dominated dusts that they also collected. So there is potentially some link between the iron valence state and bioavailability there as well. And that's our data. We do get quite a nice spread between iron 2 and iron 3. Some iron isotope data we also have. This is what we were kind of expecting at Leverett Glacier, in collaboration with Chris Mounsey actually, which is slightly heavier than zero isotopes, but we also get these really strange outliers here, which are negative 0.4, negative 0.65 per mil. And these actually coincide with some of these outburst events. So this could be an indicator of some of these long residence time meltwaters being flushed out, where things like iron reduction, microbial iron reduction, are quite important in long residence time waters. And there's also this interesting iron spring at the front of Leverett Glacier. And this iron spring becomes active during the summer when surface is active, and it drains into the river. And we also looked at the isotopic composition of that and size fractionated iron isotopic composition. And that's very different depending on which size fraction you take. So there's some interesting redox cycling, precipitation, and potentially impacts on iron isotopes going on. Rob Bracewell has done a lot of work on trying to quantify whether icebergs are sources of iron to the Southern Ocean. The Antarctic Ice Sheet discharges huge amounts of icebergs into the Southern Ocean every year. During past glaciations, you get these huge iceberg rafting events. What Rob thinks, and what we've done some work on as well, is that a lot of these icebergs can raft heterogeneous material out into the Southern Ocean, out into areas where there are iron limitation, and potentially alleviating some of that iron limitation naturally. And there's a paper that came out a couple of years ago by Pratt et al., which actually used satellite imagery and ocean color to track large icebergs and phytoplankton blooms. And you see these phytoplankton blooms occurring in the wake of some of these large icebergs. So when you put all this together and you come up with some back-of-the-envelope calculations based on freshwater discharge, various studies, and iron concentrations of the Greenland Ice Sheet and Antarctic Ice Sheet, you actually get some really high numbers for iron exports to the ocean. These look very, very big, and these are actually quite controversial because when we were generating some of these budgets, we really had no idea of what happened to these iron species as they entered saline waters. And iron acts very non-conservatively as an element, and it's taken out of the water very rapidly. So we know they're important in generating large iron fluxes, but we just don't know how important that is for the marine ecosystems. Also to talk very quickly, and it will be very quickly because I am running out of time, as I usually do, but about silica. So we also looked at whether silica is important, or ice sheet meltwaters are an important source of silica to downstream ecosystems because of the importance of silica to species like diatoms. And we found a similar thing, or similar story to iron, is that there's a lot of this amorphous silica that's attached to these suspended sediments. And this amorphous silica is soluble in seawater. So we've got some of this silica, we put it into low silica seawater, some of this amorphous silica, put it into low silica seawater, and observed this increase in silica concentrations over time. And this was a very crude experiment, and definitely a lot of work is needed. But we've also identified some of these silica nanoparticles, or silica coatings on some of these particles, glacial particles, using TEM as well, and associated elements. And we tried to quantify how important that might be. And again, it's a similar story to iron. There's a lot of amorphous silica attached to these suspended sediments that's being exported into the oceans. But the big question then is whether that's actually important, whether that amorphous silica dissolves on a timescale rapid enough to have an influence on the marine silica cycle. We then kind of took that idea and scaled it up a little bit more, which I like to call knowledge-based upscaling. And we wanted to have a look and see whether silica derived from ice sheets was important in the past, so during the last glaciation and during the rapid breakup of ice sheets. So we looked at silicon isotopes in meltwaters, and it turns out that meltwaters have a very, very light isotopic signature. And this is the lightest isotopic signature that's been measured in running waters, in fact. During the last glacial maximum, and actually during the initial part of deglaciation, it's been argued that the silicon isotopic signature of the oceans was lighter than it was now. And previously, people have put that down to changes in utilization by diatoms. But there might actually be a story here, or we wanted to test the hypothesis that there's a story here with meltwater releasing very light isotopic signature silicon into the oceans and driving some of this change. And we have some evidence in some marine cores to look at this change downstream of where the Icelandic ice sheet was. And then we used a 3-box model, which is about the extent of my modeling knowledge, to generate estimates of what was happening during the ice sheet breakup and how marine silicon isotopes might have been changing. And we came to this kind of conclusion that, yes, ice sheet meltwaters during the big ice sheet breakup, where huge amounts of meltwater and huge amounts of sediment were entering the ocean in very short timescales, might have been responsible for around 0.06 to 0.2 per mil change in the marine isotopic signature of silicon. People have observed the total change to be around 0.5 to 1 per mil. So this is a small fraction, but it's still potentially an important fraction and might demonstrate how important glacial meltwaters could be to marine ecosystems and to marine elemental cycling. We also looked at phosphorus. I'm not going to talk about this too much, but what I wanted to emphasize is the story is very similar as well for another lithogenically derived nutrient. Reactive phosphorus yields. This is particulate phosphorus as well. So this is the sodium hydroxide extraction. And phosphorus extractions actually aren't that well calibrated, so we call this highly reactive, but it actually may take quite a long time to dissolve in marine environments. But the yields that you generate per kilometre squared of ice are actually very, very high and very similar to some of the major rivers and certainly outweigh some of the Arctic rivers. So coming on to the next part of the story is looking at fjords, and these are these big biogeochemical reactors. Recently, people have argued that fjords are super important for global carbon cycles because they bury huge amounts of organic carbon annually. And these guys are doing some calculations. They had sediment cores from lots of different fjord systems around the world, from New Zealand to Alaska to Patagonia to Greenland. And what they were finding that fjords actually have these huge organic carbon burial rates, which greatly outweigh a lot of the other organic carbon sinks. And even though they cover only about 0.1% of the ocean surface area, they might actually be responsible for more than 10% of the organic carbon burial. So these are really important in global carbon cycles, potentially. And they have very high sedimentation rates, and they usually have very high primary productivity, and they're these kind of intense freshwater, saltwater interface zones. In a number of fjords, there's also a lot of glaciers that discharge into them, so they could be having some kind of impact. And some really good work has been done on this in the past. Schroff iron concentrations across these buoyant sediment plumes and found actually quite substantial concentrations of iron get across certainly low salinity units. Laura Vertman looked at basal or benthic recycling of iron and manganese in Svalbard fjords and found this very intense benthic recycling of iron and manganese. They called it the iron and manganese shuttle. And if this iron and manganese can make it to the surface, then potentially there could be some impact on elemental cycling at the surface. And Zhang et al. I think, Tim, you're on this paper as well.
No.
Oh, not on this paper. Yeah, which is the same group as Tim. Watch them measure it. They also looked at iron across salinity gradients in Svalbard, and it was slightly more complicated in their story, and perhaps it wasn't so important in that fjord. But one thing is for sure, there's a lot of iron in these fjords, but there's a lot of iron burial in these fjords as well, which could have impacts on the benthic environment. Mark Hopwood published a paper a couple of years ago as well, looking at seasonal changes in iron along a Greenlandic fjord. And he was actually arguing that he didn't think fjords are a particularly large source of iron to the open ocean. He thinks a lot of the iron is buried within these fjords. And the fjord in question here was 150, 160 kilometers long, really, really long fjord. And he was saying not much of this iron actually gets out of the fjord. Saying that, he still found some really high concentrations of iron if you compare these to open ocean iron concentrations, which are 1 nanomolar and lower pretty much down here. These concentrations of iron are massive. You're talking tens, even hundreds of nanomolar, either in a particulate fraction rafted down the fjord, or in this called a nanoparticulate fraction, which is filtered to 0.2, I think, in this case. The particulate fraction seems to be very, very important. It has generally high concentrations, but we really don't know anything about how bioavailable it is. So even though there's a lot of iron knocking around, we don't know what it's doing to the marine biota, if anything. So we took this idea and we went to Patagonia and looked at a fjord system in Patagonia, or several fjord systems, but I'm only going to talk about one fjord system. But it's quite a nice natural laboratory because this fjord system has a marine terminating glacier and it has a land terminating glacier, and the influence of the import in these two systems is very big for macronutrient and micronutrient fluxes. And this is the area we're talking about, between the northern Patagonian icefield and the southern Patagonian icefield. This is the largest ice mass outside of Antarctica in the southern hemisphere. And this is the fjord system. These are the stations that we sampled. Here's our marine terminating glacier, and here's our land terminating glacier. And a number of other rivers entering this fjord system. These two rivers, the Rio Baker and the Rio Pascua, are quite substantial rivers. And they're fed by glaciers and non-glacial inputs, actually. And then there's the Rio Brava, which is fed almost exclusively by non-glacial inputs, so rainwater and runoff. And there's a lot of rainwater in Patagonia. I can attest to that, having spent many days camping there. And this is what we were doing. We were doing all kinds of different things, including trace mineral clean underway sampling. I say trace mineral clean. In terms of open ocean trace mineral clean, it probably wasn't. But in terms of near coastal trace mineral clean, we think it was, and we have some good blanks. And we had these lab-on-chip underway sensors, which are these really cool macronutrient sensors developed at the National Oceanography Centre in Southampton in the UK. We had a collaborator called Alex Beaton who's running these. We had a nitrate and phosphate sensor, and these were sipping off samples every 5 or 10 minutes to do in situ measurements of nitrate and phosphate as we did underway sampling around the fjord. And we also took some gravity cores to do some pore fluid sampling and to take the sediment and try and look at the sediment mineralogy with respect to iron and manganese and organic carbon. So iron, I'm going to shuttle through these fairly quickly because, again, I'm running out of time. But iron, similar story to what other people have found. Very, very high iron concentrations in this fjord. The salinity is very, very low in the summer season. So we went in the summer and we went in the winter. There's a freshwater plume, a low salinity freshwater plume that actually goes all the way to the end of the fjord in the summer. And this freshwater plume is about 5 to 10 meters deep. And it's coming from this intense melting of the ice sheets and also some fairly substantial riverine inputs. There's lots and lots of sediment in this fjord as well. So the primary production rates in this fjord are actually relatively low because a lot of the primary producers are light limited. But there is certainly large amounts of iron. One thing I was surprised about is this dissolved iron. This is 0.02 filtrable. Some of these concentrations are pretty bonkers high. And when I first saw these, I just didn't believe them. I thought we contaminated all our samples. And that might be the case, off record, but on record, because it's on YouTube. But we also looked at these and we compared them to DOC concentrations because this phase is sometimes related to organic ligands. There's a particular iron concentrations which are super, super high. And this is what that looks like. This is one fjord, this one. This is actually the non-glacial fjord, fed by this non-glacial river here. And this non-glacial river is what we call a black water river, very, very high organic carbon concentrations, pretty high iron concentrations as well. And actually that's leading to this very high truly soluble or truly dissolved iron concentration in that fjord. And that's, seems to be related to the DOC concentrations. So there could be a key role that's being played there by organic ligands, we think. When you get into the glacial fjords, actually that truly dissolved concentration goes down pretty low, only a couple of nanomolar. Manganese does something completely different, really. Manganese is pretty much all in dissolved form, so that 0.02 filtrable form, so truly dissolved manganese, apart from these very low salinity glacial meltwaters, which also have some colloidal nanoparticulate manganese. And there's still a lot of particulate manganese knocking around in these fjords as well, due to the high amounts of sediment that are in the water. Macronutrients play a key role in a lot of this because these fjords seem to be places where you get a huge amount of micronutrients, anyway, what we found and what other people have found. But the phosphate and the nitrate concentrations tend to be very, very low. And nitrate in particular is thought to be the key limiting nutrient, or nitrogen anyway, is thought to be a key limiting nutrient in a lot of these fjord systems. This is where the difference in land versus marine terminating glaciers comes into its own, really. A lot of work has been done by Lorenz Meyer in Greenland, and he's done some really nice work on this, looking at the physics, really, of these two glacial systems and how that impacts things like upwelling in fjords. Marine terminating glaciers discharge at depth, and these very fresh plumes rise to the surface, and as they rise into the surface, they intrude deep waters, and these deep waters have a lot of nitrate and phosphate in. So actually in fjords where you get marine terminating glaciers, you get this kind of perfect combination of lithogenically derived nutrients or micronutrients and these kind of marine macronutrients that are upwelled to the surface. And you tend to get very high rates of primary production in these kinds of fjords. We also measure nitrogen with these lab-on-chip sensors. So this is our underway measurements, so taking a sample every 15 minutes or so. And we found similar kind of things, very low nitrate concentrations in most of the inner fjord where the freshwaters are entering. All the rivers we sampled in the inner fjord have very, very low nitrate concentrations as well. So this isn't particularly surprising, perhaps. Once you get into the outer fjord and the salinity increases and you get more marine water, this is kind of like the Goldilocks zone for me. This is where you have less turbidity, more macronutrients coming from the oceanic waters, and also the micronutrients coming from the freshwaters. So this is where you get higher productivity as well. We also benthic environment to try and tie together the surface and the bed. As I said, we took some sediment cores, and this is what we found from the pore fluids. I really want you to concentrate on this section here. This is where our iron and manganese concentrations are. These are the surface concentrations, or surface of the sediment core and the kind of sediment water interface. And they look very low on here, but the scale bars are very, very high. This is in micromolar. And as I was talking about nanomolar earlier, this is like several order of magnitudes higher than that. And you get this really intense zone of iron reduction or iron recycling, and the pore water is absolutely loaded full of iron. And as we're extracting the pore waters and they oxidize, you can see these pore waters going orange in the syringes. And same with manganese. There's huge concentrations of manganese. I've done a quick literature search on this, but I couldn't find any concentrations of manganese in the literature that were, anywhere near this high. And there's quite a bit of literature on pore fluids from glaciated fjords. Well, I say quite a bit. There's 3 publications, which is more than I thought there would be when I started this work. But Laura Vermans from Svalbard, Monian and Al from the Antarctic Peninsula. And they see some sulfate reduction, which we don't see in our sediment cores. We just see a lot of iron reduction and manganese reduction. But our iron concentrations tend to plot on the higher side compared to these values. And our manganese concentrations plot on the very high side compared to these values. And also on the very high side compared to a lot of other coastal sediments as well, like marginal sediments. And that kind of brings me to the end, but just to summarize, hopefully I've managed to convince you that glacial meltwaters are potentially important in coastal ecosystem elemental delivery anyway. The reactive particulate fractions dominate this export on these suspended sediments because of the intense mechanical grinding of bedrock. Big question is, are they utilized, even the surface, directly or indirectly through benthic recycling of some of these elements and then that being pumped to the surface? The transport and processing across salinity gradients in fjords or in near coastal ecosystems like riverine systems is very, very important. Fjords are very productive. We really don't know what influence glaciers might be having on fjord carbon sinks. I think there's a lot of work to do there. But fjords do appear to be carbon burial hotspots, so I think we need to do more work to quantify exactly how important the carbon burial hotspots are and how these might change in the future with increased warming, especially in these glaciated environments. And we really don't understand the importance of benthic recycling very well in these glaciated environments either. I mean, there's not very many papers, and there aren't very many sediment cores that come from fjords that are currently glaciated. We don't really have a clue at all what's going on in Antarctica because there's a distinct lack of samples for iron concentrations anyway in subglacial lakes. So as part of my postdoc, part of that is to try and quantify how important subglacial ecosystems in Antarctica might be in delivering iron to the Southern Ocean, which is iron limited as well. So they could be very important, and we really don't have any grasp of how important. Happy to take questions if people haven't fallen asleep.